Hello. You recall that we have defined two events A and B as independent if probability of A intersection B is equal to the product of their probabilities. In other words, we call two events independent if probability operated over in intersection becomes product. Now we want to extend this definition to random variables. And you recall also that for a random variable x, we defined this as an event. And for a random variable y, we define these as an event. Now, we want to extend this definition of independence and say two random variables are independent if any events created by random variable x and any other events created by a random variable y are independent. In other words, these two events should be independent not only for one fixed value of x and one fixed value of y, but for all x and for all values of y, these two events should be independent. So in other words, this probability shall be equal to product of their probabilities. So for two random variables be independent, it is not enough that only one event x smaller than x be independent of y being smaller than y for one fixed value of x and y, but for all x and for all y, we should have these two independents. Let's say this is event A, which is a function of x, and this is event B, which is a function of y. So if these two random variables are independent, probability of their intersection is the joint CDF, and probability of A is this guy, and probability of B is this guy. So we call two random variables independent if we have if we could decompose the joint CDF is equal to marginal CDF of x times marginal CDF of y. So CDF of CDF of x times CDF of y. So this decomposition should be valid for all values of x and y with no exception anywhere in the set. So these independence, in contrast of independence of two events, which is simple, independence of two events is just one equality, but independence of two random variables is not just one equality, is an equality which should be satisfied for all x and y. So if you take partial derivative of these with respect to x and then partial derivative of these with respect to y, this becomes the joint PDF. So here you see that joint PDF becomes equal to product of the marginal PDF. In other words, it is necessarily and sufficient that you could decompose the joint PDF or the joint CDF. Doesn't matter which one, because this relationship is one-to-one. So we could have used these as definition, or you could use these as definition. They are equivalent. So let us have one example. We say that a bivariate jointly normal distribution, they are independent if their autocorrelation or correlation coefficient is 0. So this is a theorem. So you remember that a joint normal distribution had a long expression with f xy of x and y was equal to a constant, okay, a constant, and e to the power of minus 1 over 2 something, and then you had a long expression. In this expression you had x minus mu x to the power of 2 times something plus y minus mu y to the power of 2 times something, and then minus a constant, and then x minus mu x times y minus mu y. So if you want to be able to show that this is equal to the marginal distribution, which is fx of x, which is 1 over a square root of 2 pi sigma 2x, and then e to the power of minus x minus mu x to the power of 2 divided by 2 sigma 2x, and then times similar expression for y, you could see that if these must be equal to that, you could conclude that rho x y must be equal to 0. So independence for a jointly normal, so if you have independence plus jointly normal, then you have rho x y equals 0. So this is one side of this theorem. Moreover, if you have rho x y is equal 0 and independence, then you have if you have rho x y is 0 and you have normal, joint normal, then you have independence. So as soon as we know they are jointly normal, independence means that rho is equal to 0.